All right, so we just finished talking about how we can break vectors into pieces, right? Because this is moving in two directions, both horizontally and vertically, we can break it into those pieces, horizontal and vertical, and that's the same as the combined motion. Does that make sense? But what if I were to give you multiple vectors, and you have to take those multiple vectors and break them into pieces? Could we use those pieces then to find our overall resultant? In other words, can I add these vectors? That's what we call this, vector addition. Okay? So we'll start by doing exactly the same thing that you all have done in the past. If you want to go with me in your textbook, this is in 5.1. We're looking very particularly at page 227. Is where we're kind of breaking down these pieces here. Okay? 127? 127, excuse me, not 227. 127. So are you comfortable? I can take these three vectors, and since all three of them are moving both horizontally and vertically, I can break them into their components, like this. Red being X components, Y being blue being Y components. Make sense? And then I can take all of those pieces, all of the X's and all of the Y's, and I can line them up and add them together. How do I add components, or how do I add vectors? I put them tip to tail. You remember this, right? The end of one with the beginning of the other. So when I put all these guys together, and of course these angles are going to keep their same angles. These vectors will keep their same angles. I don't move their directions. I end up with something like this. Are you with me so far? Okay? I took the pieces, I lined up all the X's, because in this case all the X's were going in this positive direction to the right, correct? And all the Y's were going in the positive direction to the north, or to upward, right? So therefore, I just simply have to add them together. Are you comfortable, instead of having this jig-jaggedy line here, I could just make it one line, and that would be the resultant. If I did all three of those motions, the result of that would be the green line. Does that make sense? And we call the adding of all of these X's together, we call that the resultant in the X direction. And we call this the resultant in the Y direction. Question?
So your R is basically like an average kind of to the direction?
Sure. It's taking into account all of the pieces together, and this is the total motion that you do is the R. Does that make sense? If you want to go average, I'm okay with that. Well, you notice that if I take and I put all these guys together, it does actually take me the exact same distance as if I just made one line. Does that make sense? Yes, because you're adding the pieces, the components of it together. It would be. Because again, these are combinations of both going up and over, up and over, up and over, right? And I'm taking this, putting the same piece here. It'll be the same displacement. If you want to go the actual physics terms, you've actually left the same distance from your origin, but you traveled longer distance. I would agree with that. I would agree with that. Right. Displacement from the origin to where you are. Does that make sense? But you went a further distance. I would completely agree with that. We're cool. If I wanted to actually calculate the numbers for R, right? If I wanted to actually get a number for R, are you comfortable? I'm just going to use Pythagoreans. That R is the square root of the Rx squared plus Ry squared. And my program doesn't give you a full square root. It just gives you a little front symbol to it. Just so you know that all of that will be included underneath that radical. We're cool so far? Concepts are solid. If I want to know what this angle is, what this theta is, this is the first time I'm going to use tangent. Right? We use cosine and sine to find x's and y's. But in this case, since I know my Rx and I know my Ry, I'm going to use tangent, which is opposite over adjacent, to find us that angle. Does that make sense? And because if I write that tangent of theta is equal to opposite over adjacent. Well, I know opposite, I know adjacent. I want to find tangent, right? So therefore, I have to divide by tangent, which means that theta is equal to the inverse tangent of opposite over. Does that make sense? That's where that tan -1 came from. Because I had to get the angle on its own, so I had to divide by it. And on your calculator, I'm sure you've seen this before, that there is, if you push the second button usually, where it says tangent, there's an inverse tangent just on top of that, tan -1. Are you with me so far? And my trouble with what I did previously was this is where I stopped, and I gave you all some problems and you were to apply this. But I want to show you how this works in an actual problem, okay? Because there's a process. That process is given to you there on page 127. And it's a decently in-depth process. The steps are pretty straightforward, but you have to go through this whole 6-step process to solve a problem like you'll do in number 5. Okay? We won't do this for every one of the homework problems, but at least the first one, it knocks you right off the bat that you got to follow the whole entire piece. And that's again there on page 127. So we start by choosing a coordinate system. And for most of the problems we do, up is positive and to the right is positive. Why? Because left must be negative, right? Left-handed folks, it has to be negative, right? Down is, of course, always negative. But for whatever reason, right's positive, left's negative. That's just the way we do it. But if Autumn wants to choose right to be positive, sure, that's fine. Or right to be negative, sure, that's fine. Whatever you want. So you choose your coordinate system. You're going to find the x and y components. Are you comfortable that that's what we did yesterday, right? You had a vector, you broke it into its pieces. Then we're going to take and we're going to add all those x's and all the y's to get the two resultants, the ry and the rx. Then we're going to use Pythagorean to find r. And then we're going to use that formula for the angle to find the angle of r, the inverse tangent to find that. So that's a summary, basically, of what I just showed you a moment ago. We're cool still? Question?
So, I don't know if you're going to cover this after, but how does the vector addition with all the different lines work if they're going in opposite directions?
Sure. I'm going to show you one right here. Let's do that. Yep. So here are 3 vectors that I'm giving you. If you care, this in your textbook, I think it's number 11. And 11 and 12 and 13 is all pieces of what I'm doing here. So I've got 3 lines here, right? K is going 4 to the left, which in this case would be negative. Does that make sense? Because I've said that my coordinate system, up is positive and right is positive. So therefore, left and down are negatives. So since this vector is going to the left, we give it negative 4.0. It doesn't mean it's bad, it just means it's going opposite of positive. We cool? Vector M is 5.0, and this guy is at an angle, 37 degrees from the horizontal. And vector L is going to the right at 6.0. No units, by the way, you notice. So we don't know if it's kilometers or meters or miles, or we're just going unitless here. Okay? So again, to go back to my plan, I've chosen my coordinate system. The next step I'm going to do is find my components. So, are you comfortable that K is only moving in one dimension?
That's not possible.
It is. It's only moving in the x. It's good. It's good. It's only moving in the x dimension. So therefore, there's no need to break it into components, right? Because it's only going in one direction. It's not going up and over. It's simply going over. Does that make sense? But if you want to actually put a number on it, Its x is negative 4. You guys, you're going to have questions about this, and you're going to come ask me, and it's going to make me annoyed. Okay? Please. Thank you. Negative 4 is our x, and y is our 0, because there's nothing. We've got no up and down movement. We cool? Same thing for L. Notice it's positive, though, right? Because it's going to the right. It has no up and down, so therefore its y is 0. Question? This is what they gave you. Yep. So they gave you a vector that has some sort of magnitude and a direction. In this case, there's no angles because it's just going directly east or directly west.
Those are the different directions it's going, right?
Yes.
And then what's that angle?
This?
Yeah.
Is telling you that this vector is going 37 degrees.
Oh, so there's two vectors. Okay.
You got it. Now, you will hear them say in your reading, in your textbook, or in their problems, how they would describe this motion sometimes is they would call this 37.0 degrees north of east. Here's why. Here's east, right? And you've moved 37 degrees north of that. Does that make sense? You can use, the other way they do it is that this is 0, this is 90, this is 180, this is 270, and this is 360. So that's another way that physics will do their angles, is they always start at 0 on the positive x-axis, and they go counterclockwise around. Okay, so that's another way. Your textbook shows that to you in lovely detail there on page 126, where they talk about the quadrants. Okay, we're good so far. So K and L we've already made our components for. Let's look at M. M, I need to break it into two pieces, right? The red being my x component, the blue being my y component. To find x, it's an adjacent, so I take cosine, and I get 4.0 is my rounded, 3.99, but we round to 4.0. For the y's, it's my opposite, so I'm going to use sine. The sine of 37 times 5, and that gives me 3.009. I round it to 3.0. Again, exactly what we did yesterday. We cool? No differences of what we did yesterday. Nothing at all different. Here's where we start doing the new stuff. And all of that is, again, going back to what so we've already done 1 and 2, correct? We're now going to add all the y's and add all the x's. So, the only x's that I have are 3 different pieces, right? I've got this negative 4, I've got this positive 6, and I've got this positive 4. So to answer your question, Josh, I add them, but I just keep the sign, right? So negative 4 plus 6 gives me 6. And this is my resultant in the x dimension. I've taken all the x components, all the x pieces, and added them together. Where did I get those x pieces? From these 3 vectors they gave me, right? 2 of them only have x's, and 1 of them I had to find that x. We good so far? And notice I'm going to make a triangle with the resultants. So here's my Rx that was 6.0. And 6.0 is a positive thing, so my vector is moving to the right. If it was a negative 6.0, it would be moving to the left. Cool so far? After I find my x's, I find my y's. Now, in this case, how many y components do I have for this problem? I just got 1. All I got's that 3.0. So all I do is add 3.0. Like there is nothing to add to it, right? The other 2 lines had no y's, so therefore it's just 3.0 is my ry, my resultant in the y direction. Does that make sense? And I changed these to black. I meant to do on the other slide as well. So you could see, hey, those came from K and from L, respectively. So here's my resultant triangle. Are you with me? This is the triangle that it's all the X's and all the Y's together. And instead of using these three lines, I'm making my R, my resultant, which is the total displacement that this triangle has undergone. Are you with me? Okay? I've taken and found my X's and Y's, and now I've simply added them together and made a new triangle. Can we then find out how much that R is? Like, can we actually find out that amount? I'm going to use Pythagoreans, right? 6 and 3 on one side, let's actually plug it into the equation. And say that R is equal to the square root of 6 squared plus 3 squared. And so therefore, when I do that math, I get 6.708, which I'm going to round, that should be 7.0. My apologies, that should be 7. Let me just change it quick. Where are you? There you are. Okay, so that tells me my R is 7.0. Are you with me there? No difference in what we did before. We're just simply using Pythagoreans with the X and the Y resultants, the adding of all of the X's and Y pieces to find that new resultant. And what that is that's the summary of the motion. If you take all three of those vectors and put them into one vector, this is our motion. This is the result.
I don't know if that's just for this particular problem, but why is 6.7 rounded to 7 instead of just leaving it 6.7?
Good question. I don't know why either.
6.708.
Yeah, no, it should be 6.7. You're good. Thank you. Thank you. I don't know why I did that. I was just getting crazy with my point zeros. My apologies. Are we good? I was thinking the 0 after it. I don't know why. Anyway, it's good. We're good so far? The only thing that's remaining, so again, if we go back to our list, right? So we found our pieces. We used Pythagorean number 5 to find R. The only thing left is to find out what is the angle. What is the angle of this thing? So we found our R. Now, let's find our angle. So since I'm looking for this angle right here, tangent is opposite over adjacent. Opposite is 3.0. Adjacent is 6.0. I do the math, 26.565, which we round to 27. So therefore, want to make sure you see this, guys. So therefore, my answer for this problem, when I am taking and adding all of these three vectors together, the addition, the sum, the resultant of all of these vectors is 6.7. And what angle is that going? At 27 degrees. Are you with me? Okay? Understand that if one of these triangles was going opposite, like how this is going opposite, it's going west instead of going east, then you have to make sure you keep the sign. Okay? If my resultant, let's say my resultant here would have been -6, my triangle would be flipped the other way. Right? It would be a -6, so moving to the left and then going up 3. What if my y was negative? Well, it would go positive for x and then downward for y.
What is it? How do you,
If you had two negatives, it'd be going right and down.
how do you do it so that the x is negative?
X was negative would be going to the left.
So that's just like the way the angle is at.
Yep. This is positive and positive. Yep. Are you with me, my friends? Question.
Let's say, so right there, that's like a, what, 45-degree angle?
No, it's a 27-degree angle.
Oh, you're 27, so let's
Did I draw it closer to a... Yes, I did draw it closer.
It was
Right, what you'll find is if you do this, if you draw it so that you're in the right coordinate plane, so positive, positive, negative, negative, okay? So again, let's say that this would have been -6. I would have drawn it over 6, up 3. And this would be my theta. So it would still be a number less than 90. Right. Because we're taking into it, we're changing the direction that we go based on the signs of my components.
No, but like, okay, so you can't write it in positive and have an opposite.
So you could theoretically, I hear where you're going. Let's say that this was 30 degrees here. You could have written it as 160 degrees. Right? Starting at 0 here and going all the way around. You could have done that, and I would have accepted that. Because again, some of you like to do it that way. I'd be fine with that. Okay? But in this case, you could have said 30 degrees north of west, and I'd be cool with that too. Does that make sense? Your textbook loves to use the directions, the cardinal planes, north, south, east, west. They'll use those for a number of different pieces.
So on this type of problem, we're solving for their displacement after.
Sure, right. What is the final displacement they have moved from the origin? Yep. Yep, I would agree with that completely. Maybe potentially, theoretically, hopefully. All right. All right. Well, this is, again, I don't always see your faces looking nervous. So again, here's our plan, right? Coordinate system, find components, do the x and the y components, you add them together, keeping the signs in mind, don't forget the signs. Use Pythagorean to find r, and then use our inverse tangent to find the angle. There's your assignment. 5 to 9. Let's jump into it.